Now in 6.4, we're going to start looking at the derivative of ln of x, and also we'll focus now on what we can do with logs and exponentials of other bases now that we've discussed how to find the derivative of ln x. Well, let's start with the proof of this formula that we have here, that the derivative of ln of x is equal to 1 over x. And a good way to start it is to start with letting y equal to ln x. So now essentially our goal is to find a formula for dy dx. One thing I can do is I can interchange this now into its exponential form. So we know that y equals ln of x can be written as x equals e to the power of y. And now I can differentiate the two sides of the equations. So we got d dx of x on the right side equals d dx of e to the y on the right side. And now on the left side I'll have 1. On the right side I'll have the derivative of e to the y will be e to the y. And then because we're taking the derivative with respect to x, we'll multiply by dy over dx. And so isolating dy over dx, we get 1 over e to the y. And then going back to this step up here, we saw e to the y is really just equal to x. So we have dy dx equals 1 over x. Okay, so that establishes this very simple derivative formula for the natural log of x. So let's practice this formula. When I want to take the derivative of ln of x cubed plus 1, for instance, well, we know it's going to be 1 over x cubed plus 1 times the derivative of x cubed plus 1. Of course, here we're just applying the chain rule, which leaves me with the derivative of x cubed plus 1, 3x squared in the numerator, over x cubed plus 1. So with that in mind, we can kind of adjust our derivative formula a little bit to accommodate the chain rule. Right? Say, for instance, I want to take the derivative of ln of some function u. Well, of course, this would be 1 over u times the derivative of u. Or maybe it's more clear if I think of it this way, that if I've got the derivative of ln of some function g of x, this would be 1 over g of x times the derivative of g of x, which here I can just put in the numerator as g prime of x. And you see that's kind of exactly what we have here, right? It's g prime in the numerator was 3x squared, which was the derivative of the inside of the logarithm, over x cubed plus 1. Let's practice that with this example. Ln of sine x, we know this would be 1 over sine x times the derivative of sine x, which we know is cosine x. So we have cosine x over sine x, which is just cotangent. And notice in a way what we've done is we've stumbled across the antiderivative of cotangent, right? So now if I were to ask what's the antiderivative of cotangent, well, in a sense, we've kind of solved it backwards here, right? It's just ln of sine x. What about this function here, ln of x with the square root over it? Well, think of this now as the ln of x has a power of 1/2, so we'll do the outer function first, 1/2 times ln of x to the negative 1/2 on the outside. And then we'll times that by the derivative of ln x. Right there again, we're applying the chain rule. And of course, the derivative of ln x would be 1 over x. So let me rewrite this first part as 1 over 2 times the square root of ln x times the derivative of ln x, which is 1 over x. Okay. Or maybe a nicer way to write this, right, 2x square root of ln x here in the bottom. Let's try this example. What I notice here is we've got the derivative of ln of x plus 1 over the square root of x minus 2. Since I've got a quotient inside that logarithm, before I take the derivative, what I might want to do here is apply a property of logarithms that makes this perhaps a little bit easier to differentiate. In this case, because I've got a quotient inside the logarithm, we can split it up as ln of x plus 1 minus ln of the square root of x minus 2. Right? That's our property of logarithms, that if I've got a quotient ln of a over b, I can write that as ln of a minus ln of b. So that actually looks a little bit easier to differentiate now, because I can now do them separately, as opposed to the form that it's in here. I would have to consider the quotient rule. But now I no longer have to worry about using the quotient rule. In fact, I could go a little bit further simplifying this, because here the natural log of the square root of x minus 2, we can write that as ln of x minus 2 to the 1/2 power. And then I can use that property of logs that allows me to bring that 1/2 out in front. So again, here I haven't done the derivative yet, so we'll do that in one more step. But doing this last little simplification actually reduces the complexity of the derivative quite a bit, because now what was the square root originally is now a factor of 1/2 in front of the log. And so taking its derivative is much simpler, because now I can use the constant multiple rule, which says I can just skip over that constant multiple and look at the derivative of ln of x minus 2. And I can do each of these terms separately. And so my derivative now is very simple, 1 over x plus 1 minus 1/2 times 1 over x minus 2. In fact, here I can just write this as 2 times x minus 2. Okay, so notice that this was perhaps simpler than having to use the quotient rule by leaving it how it was originally written. Using these properties of logarithms to split them up into separate terms, and then taking any powers in front of the log as a multiple, constant multiple, allows us then to get a much simpler derivative. You can check that if you were to do this directly, you would perhaps get something maybe a little bit different than what we see here, but it would be equivalent, an equivalent answer. Just maybe a little more complicated, because then you're using the quotient rule. Let's try another example, where here we're asked to find the absolute minimum value of the function f of x equals x squared ln x. So if we're finding the absolute min, we'll start by finding our critical values. So we'll take f prime and solve one that's equal to 0. Now, of course, here we're going to have to use the product rule. So we'll have the derivative of x squared is 2x times ln x without taking a derivative, plus x squared times the derivative of ln x, which is 1 over x. So here the x squared divided by x will simplify, just x. And then factoring out an x between those two terms, I'm left with 2 ln x plus 1 times x. So now when I equal this to 0, I have 2 points that I can consider. So the first one would be when x is equal to 0. And the second one would be when 2 ln x plus 1 is equal to 0. Here, if I solve for x, let's see, I would subtract the 1, divide the 2, and get ln of x equals negative 1/2. So switching this to its exponential form, I have x is equal to e to the negative 1/2 power. So the question is, which of these points would we consider to be the absolute max, or in this case actually the absolute minimum? Since x equals 0 is not in the domain of our function, notice that our function here can only consider values of x that are greater than 0, right? Since ln of x doesn't consider x equals 0 part of its domain. So we wouldn't consider x equals 0 as a critical point. So we really only have this one critical point at x equals e to the negative 1/2 power. And we can quickly check that what we have here is an absolute minimum at that point by noticing that f prime, if I take a value that's, say, less than e to the negative 1/2, substitute that in here, we would get a negative value. And if I take a value that's greater than e to the negative 1/2 and substitute that in here, we'll get a positive value. And so what we see is that our graph will be decreasing from 0 to negative 1/2, e to the negative 1/2, and then increasing beyond that. In fact, that would be going till infinity there. So it'll be decreasing on the interval from 0 to e to the negative 1/2, and then increasing on the interval from e to the negative 1/2 to infinity. Therefore, we have an absolute minimum at x equals e to the negative 1/2. And so the absolute minimum would be what we get when we substitute that into the original f. So e to the negative 1/2 squared times ln of e to the negative 1/2, which I think that would just leave me with here e to the negative ln of e to the negative 1/2 would just be negative 1/2. And then e to the negative 1/2 squared would just be e to the negative 1. So I can write this maybe as negative 1 over 2e.